Hello everyone. So today we will start with session 2 of S block elements. Today we will deal about the chemical properties of group 1 elements. Students can drop down their names for attendance purpose. We will be starting in a while. Students are requested to drop down their names for attendance purpose. We will be starting in a while. Okay. So we'll start. See, first we will study about the reducing nature, right? So alkali metals are strong reducing agents. So what are reducing agents in terms of electron? In redox, you will learn about the reduction and the oxidation power in terms of electron in detail. But here we will just have a gist. So oxidation is loss of electron, right? And reduction will be gain of electron. Reduction will be gain of electron. Oxidizing agent will gain electron. That means it itself will get reduced and oxidize the other species. Similarly, reducing agent will lose electron. That means it will get oxidized itself and reduce the other species, right? So here we are saying that alkali metals are strong reducing agents. Strong reducing agents means that they will lose electrons, right? They will oxidize themselves and reduce the other species. So if you compare the reducing nature of group 1 elements, you will find out that lithium is the most reducing one and sodium is the least powerful one. Okay, so we compare the reduction nature or the oxidation nature by the electrode potential value. Details you will learn in class 12th chemistry, that is electrochemistry chapter, right? Here you just need to remember this thing, that electrode potential, this is the reduction electrode potential. See, M plus M, and here the value of electrode potentials is given, right? So what does this mean? That how readily M plus will gain electron to be converted into M, right? This is known as the reduction potential. So positive the value of reduction potential, that will mean that M plus will gain electron. That means it will undergo reduction, right? So here you can see that there are negative values. That means instead of reduction, these will undergo oxidation and they will tend to reduce the other species. Okay, this much you should know. So here if you see, the more negative the electrode potential, that means it doesn't want to get reduced, rather it will prefer oxidation of itself, right? So here you can see for lithium, the highest negative value is there, that is minus 3.04, and for sodium it is the least, that is minus 2.7. So negative will indicate that they will oxidize themselves and reduce the other species, right? So here you can say that lithium, because it is having a much negative reduction potential, therefore it will oxidize itself and reduce the other species and it will act as a reducing agent. And similarly for sodium, because it is having the least negative value of electrode potential, that means it will tend to reduce itself in comparison to lithium. Here we are doing comparison, right? Between lithium and sodium, if you will compare, lithium will tend to oxidize it more rather than that of sodium. I hope this is clear. Now the standard electrode potential, this electrode potential which basically determines that how easily a species can get reduced or how easily a species can get oxidized, depends upon, first, from solid to gaseous. Metal will be converted from solid to the gaseous state. So this will be known as sublimation enthalpy. Then from the gaseous state, the metal will lose electron. This is known as ionization enthalpy. And then this M plus will get hydrated by water and will form aqueous solution of M plus, that is known as hydration enthalpy. So electrode potential depends upon three factors, that is sublimation, ionization and hydration. So if you compare the ionization energy, the ionization of lithium is very high, right? Because it is having small size. But because lithium has the highest hydration enthalpy, which is negative in nature, right? Hydration enthalpy is negative. However, the ionization enthalpy is positive. Right, so it is having a negative electrode potential, highest negative electrode potential. Why? Because its hydration enthalpy is very much high, right? Because we know that hydration depends upon the size of the ion. Smaller the size of the ion, greater is the hydration, and therefore the release in the hydration enthalpy will also, or the release in the hydration energy will also be more negative, right? So lithium being the smallest of them all, so it will get hydrated first, right? It will get hydrated readily and it will release a lot of amount of energy on hydration. That is why the electrode potential of lithium is the most negative, okay, which accounts for its high reducing power. High reducing power will mean that lithium itself will get oxidized to lithium plus and it will reduce the other species which is present. Now this is the question. You are given that E0 Cl2 to Cl minus. You are given the reduction potential as 1.36. From I2 to I minus, you are given the reduction potential as 0.53. From Ag plus to Ag, you are given the reduction potential as 0.79. And from Na plus to Na, you are given it as minus 2.71, and from lithium plus to lithium you are given minus 3.04. You have to arrange them in decreasing order of reducing strength. That means which will first act as a reducing agent, that will be placed first, then second, then third, then fourth, and the last one will be that will tend, which have the least reducing strength. That means it will not readily reduce the other species. Okay, anyone with the answer? I'll give you a hint. Negative the electrode potential, stronger the reducing agent. The more negative the reduction potential, stronger is the reducing agent. Now you arrange them in decreasing order of reducing agent. Which will come first? Anyone with the answer? The negative the reduction potential, stronger is the reducing agent. So here you can see that lithium is having the highest negative reduction potential, right? So we will find out the answer. Lithium will come first, then -2.71, so sodium, then 0.53 I minus, then Ag 0.79, and then 1.36, that is chloride, right? So this is how you can find out the order of reducing strength. Now reaction with nitrogen. So lithium reacts with nitrogen to form lithium nitride. Now except lithium, sodium, potassium, rubidium, cesium, francium, they do not directly combine with nitrogen to form their respective nitrides. Reaction with sulfur and phosphorus. So they react with sulfur and phosphorus to form their corresponding sulfides and phosphides. So lithium will give lithium sulfide, sodium will give sodium sulfide. Similarly, here also potassium plus P4 will give you potassium phosphide. Now solutions in liquid ammonia, this is a very important property. See, the alkali metals, what they do is they dissolve in liquid ammonia and form a deep blue colored solution. This, you can see that deep blue colored solution, right, which is conducting in nature. That means it is able to conduct electricity, right? So what happens here is that metal combines with ammonia to form a cationic complex, that is MnH3x positive, and the electron which is released, what happens here is that M gives M plus electron. Now this is M is also surrounded by ammonia, which is the solvent. This M plus will also be surrounded by ammonia, and the electron will also be surrounded by ammonia. This will also be surrounded by ammonia. So this will be positive, that is the cationic part, and this is the anionic part, and because there are ions in the solution, therefore it will conduct electricity, right? So blue color, why this blue color is occurring? Because the ammoniated electron absorbs energy in the visible region of light, and therefore it is imparting blue color to the solution. Remember the spectrum that we have done, electromagnetic spectrum, it consists of visible region, UV region, IR region. So only visible region, the wavelength of the light, which the wavelength of the radiation, rather not light, the wavelength of the radiation which lies in the visible region shows color, right? So here the electron absorbs energy. This electron absorbs energy in the visible region of electromagnetic spectrum, that is why it gives blue color. Now this solution is paramagnetic because this electron will be unpaired, right? So the solution will be paramagnetic. Now on standing, that means after some time what happens is that amides are formed, MnH2 plus hydrogen gas is released. That means immediately if you will form the solution of alkali metal in liquid ammonia, then you will get these two cationic and anionic species. Then after some time on standing that solution particularly, you will give MnH2 plus half H2. That means hydrogen gas will be released and a metal amide will be formed. Now these are highly conductive because of the ammoniated electrons and the ammoniated cations. This we have already studied, that cations and anions are formed which are responsible for the conduction of electricity. And due to this presence of electron, the ammoniated electron, that means the electron which was surrounded by ammonia, right? So this solution basically works as a powerful reducing agent. That means it will reduce the other species. It is popularly known as Birch reduction. In organic chemistry, you will study in class 12th. Right? You can just remember that alkali metals in liquid ammonia, for example, sodium in liquid ammonia is used in Birch reduction in organic chemistry. Now, in concentrated solution, what happens that if you increase the concentration, what will happen that the blue color will change to bronze color, right? And the solution will become diamagnetic instead of paramagnetic. So when it was of blue color, that means the concentration was low, so it was paramagnetic. Now when the concentration has increased, it is changing to bronze color and it is also becoming diamagnetic, right? So what happens here is that electron associates with other electron, they pair up basically, and therefore they become diamagnetic. Okay, when you increase the concentration, the electron gets paired up and the species becomes diamagnetic, and also the color of the solution changes to brown color instead of blue. Now coming on to the oxides and hydroxides. So this we have already done, oxides part, right? We will just have a review of this. So oxides, basically on combustion in excess air, lithium will form oxide, sodium will form peroxide, and potassium, rubidium and cesium will form superoxide, and this difference is due to their size stabilization, right? Because superoxide is stabilized by bigger cations, that is why it is stable with potassium, rubidium and cesium, while oxide is a smaller one, therefore it is stable with lithium, and peroxide is a medium one, so it is stable with sodium. Okay. Now, the increasing stability of the peroxide or superoxide as the size of the metal ion increases. That means as the size of the metal ion will increase, the stability of a peroxide or a superoxide will also increase. Why? The reason is that the large ion is stabilized by the larger cations. Larger anions will be stabilized by larger cations, right? They will form a more stronger lattice. So therefore, you can see here cesium peroxide is more stable than rubidium, then potassium and then sodium. Here also you can see that cesium superoxide is stable than that of rubidium, then potassium and then sodium. Because peroxide and superoxide are larger in sizes, therefore they are stabilized by larger cations, and already we know that down the group what happens, that down the group if you will see, size increases. Ionic size also increases as well as the atomic radii also increases. Now, oxides and peroxides are colorless when they are pure, but superoxides are yellow or orange in color, right? So, here if you will take NaO2, it is yellow in color, KO2, it is orange in color, rubidium O2, it is brown in color, and cesium O2, that is orange in color. Okay, so these colors basically you don't have to remember, but the flame test that we did, that which colors are corresponding to different metals when they are heated in a flame, that is very important from the examination point of view. Now the superoxides are paramagnetic in nature. So what is a superoxide? That is O2 minus, right? Just a second. Yeah. So superoxides are what? O2 minus. So what you have to do is that draw the molecular orbital diagram for O2 and then add one electron in it. Right? That will become the molecular orbital diagram of O2 minus. We have already done this in brief in chemical bonding chapter. So here you can see that O2 minus is also paramagnetic in nature due to the presence of one electron here. I'll again make you remember that O2 minus is superoxide, O2 minus is oxide, and O2 minus is peroxide. Now these oxides are easily hydrolyzed by water to form hydroxides, right? So M2O on hydrolysis will give you 2M plus plus OH minus. Then M2O2, peroxide always gives, basically if you are having, let us say sodium peroxide you are having and you treat it with water, then the resulting product will also be peroxide, that is H2O2 plus the hydroxide of the metal. Similarly, MO2 on treatment with water will give you peroxide plus oxygen gas plus metal hydroxide. So this is how hydroxides are formed from oxides. Now the hydroxides which are obtained, they are crystalline in nature, right? They are crystalline solids. In 12th class, we will learn about two solids, that is, one is the crystalline solid and the other one is the amorphous solid. You will learn the difference in class 12th, that what are basically crystalline and what are amorphous solid. In crystalline solid, you can see a pattern. Here you can see that the constituent particles will be arranged in a repeated pattern, right? They are arranged in a sequence, but in amorphous there is a random arrangement of constituent particles. Therefore, they are known as amorphous solid. So, the metal hydroxides are crystalline solids. Now, the alkali metals hydroxides are the strongest of all bases. See, we already know that metal hydroxides, if you see, or metal oxides, if you see, they are basic in nature, and we know in a particular group the most metallic will be the group 1 metals, right? So therefore they are strongest of all bases, and they dissolve in water with evolution of much heat. That means the reaction is very much exothermic in nature due to intense hydration. Now their basic strength. See, basic strength you can compare on the basis of ionization energy also, but you can also consider, here you can see that lithium OH. So lithium is smaller in size, right? Then sodium is bigger in size, then potassium is much bigger in size. So if I draw it like this, let us say this is OH, right? So this will be lithium OH, then more bigger will be sodium OH, then more bigger will be potassium OH, let us say, then more bigger will be not this one, more bigger will be rubidium OH, and then cesium OH, let us say, right? So what is happening here, that the bond length is increasing. If you see, the bond length is increasing, and we know that if the bond length increases, the bond will become weak, and therefore it will release OH minus easily. So it will act as a base. So here if you can see that cesium OH will have a greater bond distance, therefore the bond will be weak, and if the bond will be weak, it will be able to release the OH minus easily, therefore it will act more basic in nature. In comparison, basically if you will consider the ionization energy factor, so you can see here that cesium has a low ionization energy, right? It has a low ionization energy, that means it will easily lose electron. That means it is the most metallic in nature, and if it is the most metallic in nature, that means its hydroxide will be more basic in strength. So these are the two factors that you can consider. Both ways are correct. Now they are not decomposed on heating, but if you will see lithium hydroxide, it forms more stable Li2O. Right, so if you will compare the thermal stability of LiOH and Li2O, you will find out that lithium oxide is more stable than that of lithium hydroxide. So basically lithium hydroxide decomposes on heating to give more stable lithium oxide. Now we will study about halides. See, halides can be prepared by the reaction of the appropriate oxide, hydroxide or carbonate with aqueous hydrohalic acid. So HCl, HBr, HF or HI, they are known as hydrohalic acid. Hydro for hydrogen, halic for halogen, right? So hydrohalic acid. Now if you take an appropriate oxide or a hydroxide or a carbonate and you treat it with HCl, HBr, HF or HI, you will get the corresponding metallic halide, right? So here you can see, let us say that if we take lithium hydroxide plus HCl, lithium hydroxide plus HCl, now water will go out and it will leave you lithium chloride. This is how you can generate metallic halide. Similarly, if you will take, let us say, carbonate, we will take, let us say, Na2CO3, right? You treat it with HCl, that will give you what? NaCl, again a metallic halide, alkali metal halide. So in this way you can form halides of alkali metals. The second thing that you can do is that you treat metal with halogens directly and they will form a ionic solid, that is M plus X minus. Obviously we know that halogens are non-metallic in nature, while metal that you are taking, alkali metal, is metallic in nature, so they are forming ionic compound rather than that of covalent compound. Okay. Now the reactivity of alkali metals, if you will see, it will increase down the group. That means the cesium will be more reactive towards a particular halogen, then rubidium, then potassium, then sodium and then lithium. Okay. So if I give you a question like this, that cesium plus Cl2 and the other one is, let us say, potassium plus Cl2, which reaction will be faster? So this reaction will be faster as its reactivity is more than that of potassium. So down the group reactivity increases for a particular halogen. Now The ionic lattices that we are getting particularly, they have high negative enthalpies of formation. Now this is very important. What is enthalpy of formation? When 1 mole of a compound is formed from its constituent elements which are present in their standard states, that is known as what? Enthalpy of formation. The energy that is given out or basically absorbed during that process is known as enthalpy of formation. For example, let us say that we are having sodium solid plus, let us say, Cl2 in gaseous state. Okay, because the native state of sodium is solid and the native state of chlorine is gaseous, and we are obtaining NaCl. Now NaCl should be 1 mole here, right? Because 1 mole of the compound is formed, and here if you do balance the reaction, this will be half Cl2, right? So the elements, the constituent elements should be present in their native states. That means sodium should be in solid, chlorine should be in gaseous. 1 mole of the compound should be formed. So here we are keeping the stoichiometric coefficient of NaCl as 1. So the energy that will be released in this process will be known as enthalpy of formation. And generally, if you will see the lattices of alkali metal halides, they have a negative enthalpy of formation. That means the reaction is very much exothermic in nature. The energy will always be released. Now these are certain values or trends that you need to remember regarding the enthalpy of formation. So for fluoride, if you will take, the enthalpy of formation become less negative down the group, right? So if you will get a question like this, let us say that amongst cesium fluoride and potassium fluoride, which one will have a high negative enthalpy of formation? So you will say that potassium fluoride is having much negative enthalpy of formation than that of cesium fluoride. Why? Because delta H of formation values for fluorides become less negative as we go down the group. Okay, so lithium fluoride, if you will see, it will have the highest negative value, and cesium fluoride, it will have the least negative value. Then you come for chloride, bromide and iodide, reverse order is followed, right? So it becomes more negative as we move down the group. So if one says that cesium chloride and potassium chloride, which have a higher negative enthalpy of formation, now in this case cesium chloride will be having greater negative enthalpy of formation than that of potassium chloride. Okay. Now for a given metal, let us say the metal is same and you are changing the halogens, then the enthalpy of formation will become less negative from fluoride to iodide. For example, if we are having, let us say, lithium fluoride, lithium chloride, lithium bromide and lithium iodide we are having, right? So lithium fluoride will have the most negative enthalpy of formation, then lithium chloride, then lithium bromide, then lithium iodide. Here we are keeping the metal same, but we are changing the halogen. So from fluoride to iodide, enthalpy of formation will decrease or become less negative basically, right? I hope this is clear. Is this clear to all? Is this clear to all? You can get question regarding this enthalpy of formation, the trend that is followed by alkali metals. Now next we come on to Fajan's rule, right? So from Fajan's rule, as you must have studied in your chemical bonding chapter, that we can predict the covalent nature, right? So you can say that smaller the size of cation, larger the size of anion, that means SCLA, smaller the cation, larger the anion, greater is the covalent character. This is the statement of Fajan's rule. Greater is the covalent character, because small cation is able to polarize the anion effectively, while larger anion has the ability to get polarized by the cation. Right? So if you will compare, let us say lithium chloride and potassium chloride, here chloride ion is same, that means the anion is same, so you will compare the cation now. So amongst lithium and potassium, if you will compare, which is the smaller cation? Lithium is the smaller cation, therefore it will be more covalent than that of potassium chloride. Now here, if you compare lithium iodide, lithium bromide, lithium chloride and lithium fluoride, here you can see that the metal is same, the cation is same, but the anion is changing. That means I, Br, Cl and F, right? So we know that larger the anion, greater is the covalent character. So as I minus has a larger size than that of Br minus, and then Cl minus, and then F minus, because they're down the group, the size increases. Therefore, lithium iodide will have a more covalent character than that of others. Now, charge on the ion, basically we know that if you increase the positive charge on the cation, that will mean what? That the size of the cation will get smaller and smaller. So if you will compare Al3 plus, Mg2 plus and Na plus, you will find out that the one which is having a greater charge will be smaller in size, and therefore it will be able to polarize the anion more effectively and will be more covalent in nature. Right? So size basically will depend upon the charge also. Greater the size, greater the charge on the cation, smaller is the size, and reverse is the for anion. Greater is the charge, that means bigger the size of the anion. So these things must be clear to you in chemical bonding chapter also, right? So I'm just giving an idea here. Now for the melting points, if you will see that fluoride will have a greater melting point than that of chloride, bromide and iodide for the same metal, right? So here if you will compare sodium fluoride, sodium chloride, sodium bromide and sodium iodide, so you can see that sodium fluoride will have a greater melting point than sodium chloride, then sodium bromide and then sodium iodide, right? Now for the same halide ion, if you will compare the metals now, right? So here you can see that the one which is covalent in nature will have lower melting point. The one which is covalent in nature will have lower melting point. That means, if you can see, because we know that smaller the cation, greater is the covalent character. That means lithium chloride is more covalent in comparison to others, right? So covalent character decreases down the group if the halogen is same and the metal is different, right? Because we have learned that smaller the cation, greater is the covalent character. So lithium chloride will be more covalent in nature, therefore it is having low melting point. And as we move down the group, because covalent character decreases, so the melting point will also increase. Now all the halides are soluble in water. However, these two are very important from the examination point of view. These are frequently asked questions. So lithium fluoride is less soluble in water because of its high lattice enthalpy. That means the lattice which it is forming, the energy that is released due to the lattice formation of lithium fluoride is very high. So therefore it has low solubility. The lithium fluoride compound is very much stable. It does not dissolve in water readily, right? It has low solubility. While the cesium iodide is having a low solubility due to smaller hydration enthalpy. It is having a smaller hydration enthalpy. So there are two different reasons, right? So here you can say that the solubility, you can say that the compound is soluble when hydration enthalpy is greater than lattice enthalpy. The compound is said to be soluble when hydration energy, the mod of hydration energy is greater than lattice enthalpy. So here you can see that because it is having high lattice enthalpy, lithium fluoride, therefore it is insoluble in water, and for cesium iodide, if you will take, it is having a smaller hydration enthalpy, therefore it is insoluble in water. If you will take halides of lithium, so basically you can say that lithium halides are more covalent in nature than that of the other metal halides. So therefore they are soluble in non-polar solvent also, that is like ethanol, acetone, ethyl acetate. Even lithium chloride is soluble in pyridine also. So because of halides of lithium are covalent in nature than that of the other halides corresponding to different metals, right? So because of its covalent character, it is soluble in non-polar solvents also like ethanol, acetone and ethyl acetate. Now coming on to carbonates and bicarbonates. So lithium carbonate is very unstable. It decomposes to lithium oxide plus carbon dioxide. Now why do it decomposes? Because lithium is very small in size, right? So it is able to polarize a large carbonate ion, which leads to the formation of more stable lithium oxide. That means lithium carbonate is not very much stable, rather it decomposes to form lithium oxide. And if you will take the hydrogen carbonate of lithium, that is lithium HCO3, which is known as the bicarbonate also, it does not exist in solid form. While if you will take sodium hydrogen carbonate, sodium potassium hydrogen carbonate, right, they are found in solid form. Now the thermal stability of carbonate. See, basically you can remember that a stable compound is formed when smaller cation stabilizes the smaller anion and larger cation stabilizes the larger anion. So here you are having carbonate. So CO3 2 minus you are having, it is a larger anion, therefore it will be stable or stabilized by the larger cation. So we know that cesium has a greater size than that of all other metals. So therefore cesium carbonate will be more stable and lithium carbonate will be the least stable because it is having a smaller cation, right? So you can remember that smaller cation, smaller anion, that will mean a stable compound, and also larger cation, larger anion, that will also mean a stable compound. Okay. Now, a mixture of sodium carbonate and potassium carbonate is also known as a fusion mixture, while K2CO3, the other name is pearl ash. Now, the bicarbonates of all the alkali metals are known except lithium hydrogen carbonate or lithium bicarbonate. Others exist as solid. Lithium bicarbonate exists in solution while other exist as solid, and on heating the bicarbonates converts into carbonates. So here is an example that sodium bicarbonate on heating will form sodium carbonate plus CO2 plus water, right? Now the solubility of the carbonate and bicarbonate increases on down the group, right? So down the group, if you will compare the solubility in water, then you can have that cesium bicarbonate is the most soluble in water while lithium bicarbonate is the least soluble in water due to their lower lattice energies, right? I have already told you that hydration energy should be greater than that of lattice energy, then only the compound will be soluble. So here cesium bicarbonate is having a lower lattice energy, therefore it is more soluble in water as compared to that of the lithium bicarbonate. Now we come on to sulfates and nitrates. So lithium nitrate on decomposing gives lithium oxide plus it releases brown color NO2 gas plus oxygen, while sodium nitrate releases sodium nitrite, that is NaNO2 plus oxygen gas. NaNO3 is known as child saltpeter while KNO3 is known as Indian saltpeter. These names are very much important from the examination point of view, that NaNO3 is known as child saltpeter and KNO3 is known as Indian saltpeter. And this is the difference between lithium and sodium, that lithium gives lithium oxide while sodium nitrate gives sodium nitrite on decomposition or basically on providing heat. Now lithium sulfate it is insoluble in water, whereas other sulfates, if you will see, for example, sodium sulfate, potassium sulfate, they are soluble in water. So this is the another point of difference between lithium and the rest of the metals, that lithium sulfate is insoluble in water while the other metal sulfates are soluble in water. And Na2SO4.10H2O, that means if you associate 10 water molecules with sodium sulfate, it is known as Glauber's salt. Now you come on to anomalous properties of lithium. Anomalous properties means that how it is different from rest of the members of the same group, right? That how lithium is different from sodium, potassium, rubidium, cesium, francium. Now, what is the reason for the anomalous behavior of lithium is that because it has exceptionally small size, it has high polarizing power. Why? Because it is of small size, and we know that the smaller size cation is able to polarize the anion easily, right? And because it is a smaller cation, therefore the covalent character is also more than that of the other metals, which is responsible for its solubility in organic solvent that we have already discussed in the previous slides. Now, the points of difference between lithium and other metals is that lithium is much harder. Its melting point and boiling point are very much higher than that of the other alkali metals. Lithium is the least reactive, but still lithium is the only one which produces lithium oxide on directly combining with air and lithium nitride on directly combining with nitrogen, while other alkali metals does not show the same behavior. Now, lithium chloride is deliquescent in nature, so it forms a hydrate, that is lithium chloride 2H2O, whereas other metal chlorides, if you will see, they do not form hydrates. Lithium hydrogen carbonate or lithium bicarbonate, as we have already discussed, that it is obtained in solution form, while the other bicarbonates of metals exist in solid form. Lithium, unlike other alkali metals, forms no ethanide on reaction with ethine. I guess we have discussed this in the previous session. This is ethine gas. So, if it reacts with sodium, it will give you what? C triple bond C negative, Na plus here and Na plus here. But same is not done by lithium. So, this is a property which differentiates lithium from its other group members. Now, lithium nitrate on decomposition gives lithium oxide, whereas other alkali metals, if you will see, they give corresponding nitrates. Sodium nitrate will yield you sodium nitrite. Similarly, potassium nitrate will yield you potassium nitrite. So, NO3 minus is nitrate and NO2 minus is known as nitrite. So, lithium nitrate on decomposition will yield you oxide, while other metal nitrates will yield you nitrite. Okay, this is another point of difference between lithium and alkali metals. Now, lithium fluoride and lithium oxide, they are very much less soluble in water, while other fluorides and other oxides are soluble in water. Now comes the diagonal relationship. Now this is very important from the examination point of view. See, what is diagonal relationship? If you go diagonally, lithium and magnesium are diagonal, beryllium and aluminium are diagonal, boron and silicon are diagonal. Right? So across the period size decreases, down the group size increases, and across the diagonal, if you will say that the size remains almost similar. This is known as diagonal relationship, right? So, diagonal relationship is between second period and third period member. Lithium and magnesium, beryllium and aluminium, boron and silicon. Why it is there? Because of the similar atomic or ionic sizes, and also they have similar polarizing power, right? And they also have comparable electronegativities. So, these are the factors that are commonly shared by the elements which show diagonal relationship to each other. Now, we will study about the similarities between lithium and magnesium. So, lithium is of second period while magnesium is of third period, right? And they both show diagonal relationship because their ionic and atomic radii are almost the same. So here if you see, lithium is having 152, magnesium is having 160. Ionic radii are much more similar. Lithium plus is having 76 while Mg2 plus is having 72 picometers. So almost similar radii are there, and therefore they show similarity in their properties. So what are the properties in which they show similarities? Both lithium and magnesium are harder and lighter than the other elements in the respective groups. So in group 1, if you will compare, lithium will be harder and lighter, and magnesium will also be harder and lighter in group 2. Lithium and magnesium, they both react slowly with water, and their oxides and hydroxides are much less soluble, and their hydroxides decompose on heating. Right? Now, this is a very important fact, that they both form nitride on reaction with nitrogen, that too direct combination. So in group 1, except lithium, no one else is able to do that, and in group 2, except magnesium, no one is able to form nitride on direct combination with nitrogen. Right? Their oxides, that means lithium oxide and magnesium oxide, they do not combine to give they do not combine with excess oxygen. That means if you supply excess oxygen to magnesium oxide or lithium oxide, they will not form superoxide. Right? Rather, other metals, if you will compare in their respective groups, they will form superoxides. Now, the carbonates of lithium and magnesium, they decompose easily, as we have already seen, right, to give oxides and CO2. And also we have learned that lithium hydrogen carbonate and similarly magnesium hydrogen carbonate, which is also known as bicarbonates, they do not exist in solid form. Both lithium chloride and magnesium chloride are soluble in ethanol. This is another common factor, and both form hydrated complexes. So here you can see that lithium chloride form hydrated complex as 2H2O, and MgCl2 also forms hydrated complex as 8H2O. So they both are deliquescent in nature. Their chlorides are deliquescent in nature. So that's all for today. I think in the next class we will begin with the group 2 elements, that are alkaline earth metals. Right? So with alkaline earth metals, we will similarly deal with the physical and chemical property as we have done with group 1. Right? And then your S block chapter will be over. So that's all for today. Happy learning to all.